Have you ever thought about how you could connect, say, thousands of people directly to each other without needing a massive central server in the middle? Well, GenosRTC has a really fascinating way of doing this with its peer-to-peer module. But today, we're diving into something special, a mode you unlock with just one little parameter, RTC:cells. And that one tiny change, well, it activates this brilliant self-organizing system that we're going to break down right now.
Okay, so let's get into it. The whole promise of peer-to-peer is pretty incredible, right? You connect users directly to each other. This means you slash latency, which is absolutely critical for things like gaming or live video. You get way better privacy because there isn't some central company watching all the data flow back and forth, and maybe best of all, no central bottlenecks. The system is only as limited as its users. But there's always a catch, isn't there? This beautiful direct connection model, it works perfectly for a small group. But the second you start adding more and more people, a huge problem pops up that can literally bring the entire system to its knees. See, in a small network, everyone talking to everyone else is no big deal. It's fast. But in a large network, it's just total chaos. There's this classic problem called network flooding. Every single time one person sends a message, every other person resends it to everyone they know. What you get is this massive exponential storm of data that just eats up all the bandwidth, crashes browsers, and causes the whole thing to fail. So how on earth do you fix that? Well, you get organized. Instead of having one giant tangled mess where everyone is basically screaming at everyone else all at once, this system introduces a really elegant solution. It automatically organizes all the users into smaller, much more manageable, interconnected groups. And this is the core idea of a cellular mesh. Just think of it like a network of networks. Each little group, or cell, is its own high-performance subnetwork. By grouping people this way, messages stay local. And that is the secret sauce to stopping that global network flood we were just talking about. So how does this organization actually happen? It's surprisingly simple. Let's say you have 9 users. We'll just call them A through I. The system basically just lines them all up and divides them. If we say the cell size is 3, then the first 3, A, B, and C, go into cell 0. The next 3 go into cell 1, and so on. It's just a super clean, predictable way to bring some order to the chaos. Okay, but what if someone in cell 0 needs to send a message to someone over in cell 2? You can't just have these cells be totally isolated, and that's where bridges come in. The network is smart enough to select a few key peers to act as the official messengers between neighboring cells. They're the only ones who are allowed to pass messages across those cell borders. So the flow of a message is really the crucial part here. A message starts out local, it's only broadcast inside its own cell. Super fast, totally contained. If it needs to go further, the cell's bridge picks it up and forwards it on. But, and this is key, only to its direct neighbors. Then, to make sure that message doesn't just bounce around forever in a loop, the system cleverly tracks the ID of every message it's ever seen. That way, no message ever gets processed more than once. Pretty smart, right? But here's the coolest part. This isn't just some static layout you configure once. The network is more like a living system. It is constantly monitoring its own health, adapting and optimizing its structure, all in real time. For example, the system automatically figures out the best cell size. When the network is small with only 100 people, the cells can be tiny. But as it grows to, say, 1,000 peers, the system might go, okay, a cell size of 10 is better now. If it hits 10,000 users, it might expand the cells to the maximum of 50 peers. It's always running the numbers to find that perfect sweet spot between local chatter and cross-cell communication. This leads to a really important question, though. If these bridges are the gatekeepers for all communication, you can't just pick them randomly. So how does a decentralized network, one with no central boss, decide who gets to have such an important job? It gives every single peer a health score. And this score is based on some really simple but powerful ideas. Like uptime. How long have you been connected? A peer that's been online for a while is probably stable. Or AV-RTT. That's your average round-trip time, which is just a fancy way of saying network speed. A lone number means you're fast. And finally, have we heard from you recently? The network constantly ranks everyone by this score and promotes the healthiest, most reliable peers to be its bridges. So we've got this intelligent, self-organizing, even self-healing network. What's the actual impact of all this clever design? Well, the payoff is absolutely massive, and it all comes down to one thing: the number of connections. And wow, these numbers really tell the whole story. With just 1,000 people, a traditional mesh network needs almost 500,000 connections. That's just completely unsustainable. But the cellular mesh? Less than 5,000. Now look at 10,000 peers. The cellular model needs around 46,000 connections. The old way would require an absolutely impossible 50 million connections. The bottom line here is a performance improvement that is almost hard to wrap your head around. We're not talking about a little 10 or 20% gain. For large networks, this architecture is up to 1,000 times more efficient. This is really the key takeaway: 100 to 1,000 times reduction in connections. That is the difference between a network that sounds good in theory and one that actually works in the real world. It completely transforms peer-to-peer from a fun little tool for small groups into a serious architecture for massive applications. So yeah, this isn't just some cool academic idea on a whiteboard. This is a practical system that developers can actually tune and optimize for specific real-world use cases. For example, if you're building a real-time game, you'd want to set it up for very small, tight cells that keeps the latency as low as humanly possible. Or, building a huge chat app? Just set the cell size to auto and let the system handle everything for you. What about an Internet of Things network with thousands of sensors? You can tell it to create tons of tiny cells to keep all that sensor data nicely segmented. And that really brings us to the final thought here. This whole cellular mesh design is an incredible solution to that massive P2P scaling problem. It really proves that with the right algorithms, a network can create its own order without any central authority telling it what to do. And so that leaves us with a much bigger question. If networks can learn to self-organize this efficiently, what other centralized problems are just waiting for the right decentralized solution to come along?